Hi, I am Varun Joshi, and welcome to day 50 of our Certified Kubernetes Administrator 2025 course. This is part 2 of our Kubernetes Ingress deep dive. In this part, we shift gears and get hands on. We will set up a multi AZ Amazon EKS cluster like you will see in production, install the AWS load balancer controller, and run demo 1 where we implement path based routing using an application load balancer on AWS. So without wasting any time, let's get started. Demo 1, path based routing on multi AZ Amazon EKS cluster with AWS ALB. So what you see here is you see a control plane, and when you are talking about managed Kubernetes service, the control plane is entirely managed by the cloud provider. So if I talk about EKS's control plane, managed by AWS and hosted in a dedicated VPC, even a dedicated account. So if you see here, this is AWS owned account, and then there is AWS managed VPC. Each EKS cluster has at least 2 API server nodes and at least 3 HCD nodes. Now, these are the minimums. There will be more if there is traffic in your cluster. So understand, AWS takes care of auto scaling all these control plane components for you when need arises. AWS handles auto healing of faulty control plane nodes, patching and upgrading, high availability and scaling, security updates, and certificate rotation. So if you have been through the TLS section of this course, you know how cumbersome certificate rotation could be for all these components. Hence, it is AWS who will be taking care of all the certificates for your control plane components. Then EKS pricing. So here I want to shout out that there is an hourly charge of running an EKS cluster. So even if you have not spun any worker nodes, you will still be paying for the control plane because AWS is running these for you. There is an hourly charge. Ensure when you are done with your work, you delete your cluster. So if your aim right now to is only do demo 1 and demo 2 later, then it is suggested you delete the Amazon EKS cluster because there is an hourly charge to it. Then there is EKS data plane. Now, as the name implies, data plane is the one where you deploy your workloads and where you will be running your worker nodes. Now, this runs in customer managed account and it is run in customer managed VPC. What you see here is exactly what we will be configuring. I will be using 4 worker nodes. You can set this count to 2 and I will show you how to do it. I am running 4 because I want to show you some advanced use cases. You in your environment can only run 2 worker nodes. I have split this into 2 availability zones because I want you to understand how actual production applications are deployed on Amazon EKS. You will be leveraging at minimum 2 availability zones for critical applications, and when you create nodes, they are segregated into node groups, and each node group has an auto scaling group associated with it, which is why I have shown an auto scaling group. And in the auto scaling group is where you define the minimum number of nodes and the maximum. In my configuration, I have defined the minimum to be 4. Then here are few pointers about the EKS data plane. Consists of EC2 instances that run your workloads. We will see that nodes are grouped into node group. For example, all these 4 nodes will be part of a node group, and you have the flexibility of defining multiple node groups. Now, why would you need multiple node groups? For example, maybe application 1 requires GPU. So the node group 1 has the nodes which have GPUs, and then there is an application that runs on x86 and does not require GPUs. So you will define that node group for application 2. This is just an example. So you can have multiple node groups based on your requirements. And this is not just for, the functionality that that node group is providing. This segregation could also be based on projects. For example, project 1 is associated with node group 1, and then there is application 5 which uses node group 5, for example. So keep these things in mind. Nothing is written in stone. The flexibility is there. You will design your architecture based on the requirement that is put forward by the client. Here we are saying nodes are grouped into node groups, managed node group, and there are self-managed node groups. So we are using managed node group in this scenario, and 99% of the times it is managed node groups that are used. There are certain corner cases where compliance centric or security centric organizations may choose to use self-managed node groups. Each node group typically uses the same AMI and instance type. Now, this is the architecture that we are going to deploy. Let's do one thing. I will take you to the GitHub notes to show you certain things that you must have to perform this demo along with me. I am using T3 small, and I suggest if you are using AWS credits. Now it was 15th of July when AWS introduced this, where they said that now they will be giving 100 free tier credits for you to use, but you can only use them for specific instances. So if you try to run T3 medium with those credits, you will not be able to do so. So if you have those credits, use T3 small. If you are still in the free tier plan that was applicable before 15th July 2025, then you can use the instance types that fall under the free tier. But again, I would suggest you to use T3 small instances at minimum. Now I am using 4 nodes because I want to demonstrate topology spread constraints which rely on sufficient node distributions across AZs. So in your use case, you can only spin 2 worker nodes. These are 3 other things that you should have. Your jump host or your laptop should have AWS CLI, EKS CTL, and Helm. Why Helm? Because we will be deploying AWS's load balancer controller using Helm charts, and we have a detailed lecture on Helm. If you want to check it out, go and check it out. Now let's understand what are we going to create. So whatever we are doing, all of these things are detailed in the GitHub notes. You will see all these YAMLs here describing everything that we are doing. I'll show this file to you directly in Visual Studio Code. So let's go there. Here I am in day 49. This has the same structure as you will see in the GitHub notes. I'll open this file and this shows me the configuration. So I have 4 defined here. You can change this to 2. So what we are saying here, create a cluster for me. The name of the cluster is Cloud with Varjosh Ingress Demo. I'm using US East 2. Tags is I'm adding 3 tags. Owner is Varun Joshi, business unit is Cloud with Varjosh, project is Ingress Demo. I am using 2 availability zones here. IAM is with OIDC is true. Now if I want AWS to understand the identities that are created in my Kubernetes cluster, which are service accounts, then I want to make this true. And as we progress with this lecture, we will know more about it. I am creating only one managed group. I am calling this Cloud with Varjosh EKS private node group because the networking for this is private. Hence, I have added a private flag here. And here I'm saying minimum size is 4, maximum is 4. Private networking true, volume size is 20 GB. That is the volume that will be associated with my worker node. So I'll have 4 worker nodes with 20 GB each. IAM with add-on policy. So here I'm saying what all things my nodes are allowed to do. Now this is not something that is written in stone. You can change it once you have also configured your cluster. I'm adding labels. Lifecycle is EC2 autoscaler. If you want to know more about it, then you can always refer to GitHub notes. Now it takes 15-20 minutes to create a cluster. Hence I have already run the command that is to create the cluster. So if I go to my terminal And if I go to this screen, I only ran this command, EKS create cluster -f. I want to create the cluster using this file, and the cluster was created for me. Now if I run kubectl get nodes here, then you will see there are 4 nodes in my cluster. Now let's go to the diagrams, and I also want to show you one more thing. And here I am telling you what are we going to deploy. Let's walk this diagram from right to left. We have iPhone pods, Android pods, and desktop pods. This should be pods, pardon me. Now all of these are part of a deployment. So iPhone pods are part of iPhone deployment, Android pods of Android deployment, and so on. All of these are fronted by their respective cluster IP service. Here one is iPhone, Android, and desktop. Our aim with this demo is whenever someone writes iPhone along with the load balancer's DNS name, they should be served by iPhone pods. If someone writes Android, they should be served by Android pods. And if they do not supply anything, they should be served by the desktop SVC. So desktop SVC is my catch-all. If user has not specified iPhone or Android, then my desktop pods will cater the request. The containers that are part of these pods are listening on port 5678, and if iPhone pods are serving the request, then the user will see an iPhone related message. If someone is served by Android pods, they will be seeing an Android specific message. Similarly, desktop pods will be showing a desktop specific message. Here these are the same like we saw before. There is an ingress controller. We'll be creating an ingress resource. So firstly we will deploy an ingress controller. Very first thing will be that. Then we'll be deploying all these things step by step. Then we'll be creating an ingress resource, and as soon as we create the ingress resource, we will see that the ingress controller will get in action and deploy this load balancer for us. So the entire architecture we'll be creating from the very scratch. I want you to concentrate on this thing: nodes and pods spread across 2 AZs. So everything that you see here is distributed across 2 availability zones, especially this thing and the load balancer, because these are logical. These are across the entire cluster. But when I talk about ingress controller and these things, because these are part of deployment, they will be deployed in 2 availability zones. Now it is our responsibility that if, let's say, iPhone deployment has 10 pods, it is DevOps engineer who must be ensuring that there are 5 pods in AZ1 and 5 pods in AZ2, because I want you to know very clearly that my scheduler does not have any idea about the topology. It will schedule pods onto nodes based on resource availability, taints and tolerations, node affinity, anti-affinity, and so on. But it is not aware of underlying topology. Hence, we must find means via which we ensure that if a deployment is running, let's say 2 pods, then 1 pod is in each availability zone to ensure high availability. So with this understanding, let's start our work. I will go to my GitHub notes. I will scroll down. So cluster part we have already done, and this is the command you can use to create cluster. And then I will run this command to show you that there are 4 nodes that are spread across 2 availability zones. So here is node 1, you see 2B, node 2 is 2B, node 3 2A, and node 4 2A. So they are spread across 2 availability zones. This part is clear. And let's go back to GitHub notes and let's see what we want to do next. We want to install AWS load balancer controller. So first thing we want to do is we want to create an IAM policy. Now stay with me for some time and I'll exactly tell you what we are doing. create IAM policy, I will first download the policy using this command, and this has downloaded the policy in day 49. So if I go to Visual Studio Code, there is an IAM policy JSON that is downloaded for me. Okay, now I'll go back to GitHub Notes again. I will create the policy in your AWS account. So using this policy JSON, I will create a policy. That policy will be named AWS Load Balancer Controller IAM policy. So I'll create this policy. I'll go to the terminal, I'll paste that command, and this will create this policy for me. It says policy created. Now the next step is create an IAM backed Kubernetes service account. Now here is where the interesting part starts. So I will copy this firstly, and let me explain you what is happening. Now see, I told you in this diagram that it is the Ingress controller that will be deploying this load balancer for you. But I want you to clearly understand that this Ingress controller can only deploy the resources if this Ingress controller has the permissions to do so. So what we are doing here is the policy that we just created is a policy that has sufficient permissions. Anyone who is using this permissions policy can create this load balancer. So that is exactly what we are doing here. And in the next step, what we are trying to do is we are trying to create IAM service account. Now understand that this is an EKS CTL command. This will be doing two things for us. First, it will be creating an IAM role for me. Second, it will be creating a Kubernetes service account. And why is this important? Now what will happen is we will ask our Ingress controller pod to use this service account, and when my controller is accessing AWS APIs to create this application load balancer, it will have permissions to do so. And why does it have permissions to do so? Because the controller pod will have a service account mounted, and that service account will have an annotated role, and that role will have these permissions. So whenever controller wants to access AWS APIs, that controller pod will look at its service account, and service account will have the role that can be used to create that load balancer. And we know once that service account can assume that role, IAM role, it can have the same permissions that are available in that IAM role. And what are the permissions that are available in that IAM role? The permissions are these permissions: AWS load controller IAM policy, because that policy will be associated with this role. So what this command will do is it will create an IAM role with the required policy attached, that is this policy. It will annotate a Kubernetes service account with this role, because the controller pod has this service account mapped. But how would the controller pod know which IAM role to use when I'm interacting with AWS APIs? It knows about that role because that role is annotated in the service account that this command creates. The third point is binds the service account to the controller pod that we will deploy in the next step. So if I copy this and I paste this here in the terminal and I press enter, and I want to show this thing to you, I'll go to this AWS console. Here is my AWS console, and you can see I am logged in as a user named Varun.Joshi. This user has administrative privileges. I am not using the root user, and you shouldn't too. Here I am using an account alias. My account is called cloud with varjosh-prod. Here I will go to CFN, that is cloud formation. I will open this in a new tab. I will go here And as a result of what we just did, you see at 1834 a stack was created for me, and this stack has created an IAM role for me. And I want you to know that whatever you are doing using EKS CTL, so even the cluster creation and then the node group creation, underneath a cloud formation template gets created, and you can see the respective stack in this tab itself. So let's go here, because this is the stack which was recently created because we ran this command, and here is the name of that stack. So if I go here, I can go to resources and check that there was a role created. And if I click on this and I go to the permissions, you see this is the policy that we just created. So we are associating the policy we just created with an IAM role we recently created using this command here. That's why I said this command is creating an IAM role with this policy, and it is also creating a Kubernetes service account. And if we look at that service account will have that role annotated. This is called IRSA, IAM role for service accounts. Now, why my Kubernetes cluster is trusted to access AWS to begin with? Because you and me added this flag. We said that IAM with OIDC is true, which is the reason your Kubernetes cluster is trusted to access AWS resources. And I want to show this to you. So if I go to my browser again, I go to IAM, I'll open this in a new tab, and then I want to show you identity providers. And here you see identity provider created 59 minutes ago. It ends with 0cc1, and let me open my EKS cluster, OIDC cc1, you see. So try to connect the dots whenever you are working with something, only then you will understand. So right now we have understood why this service account was created, and I want to show this to you. If I run here kubectl get sa-n kube system, I can press enter, and there are many service accounts created, but I want you to concentrate on this one, AWS load balancer controller, which was created just 2 minutes back. And if I press the up arrow, I add a describe here, and then here I add that service account name. I press enter. You see how this works. Annotation, here is the role annotated. This is how this service account knows which role to assume when it is accessing AWS APIs to create the load balancer for you. You see the name, Cloud with Badger Ingress demo. I add on this, and it ends with FQ1E. If I go to my console, I go to IAM again, I go to roles here. Here is that role, FQLE. FQL or 1E. If I click this role, then this is the one that was recently created by our cloud formation stack. I hope this is clear. Now let's go to the GitHub repository and see what is our next step. We have done this. Now what we want to do is we want to add the repository for AWS's load balancer controller. So I'll copy both these commands. This will add the repo, and again go and watch the Helm lecture, any confusion, because we have discussed these things in detail. So we'll go here to a terminal and I'll paste these commands, and if I run Helm repo list, then it will show me that there is an EKS repository added. My Bitnami was added in our Helm lecture. So we have added EKS here. Now what I want to do is before I install this, I want to show you something. I can run Helm search repo EKS, and this will show me all the charts that are available in this EKS repository. So there are plenty of things: app mesh controller, app mesh, Grafana, and so on. But I want you to concentrate on AWS's load balancer. So let me do one thing. I will write this, and here I will grep -i for load. I think this will show me the load balancer. So yeah, here is what I want you to concentrate on. There is EKS AWS load balancer controller, and the chart version for this is 1.13.3. This is the chart version 1.13.3. Now let's see what all versions are available and which one we want to use. So I will write the same command, but here I will add this so that I can see the versions for this one. So 1.13.3 would be the latest one. So let me write this and add a versions flag here. VERSI, yeah, versions flag. And here I see all the versions. Now I want you to understand one thing. When you are dealing with production, you will not be installing the latest. You will be installing n-2, n-3, or maybe even n-1. But again, whenever you are upgrading these things, you will have to check the documentation, and not just the documentation for this controller, but the documentation of other tools that you are using, whether they are compatible with this version. And no Gen AI can do this perfectly. I'm telling you, you need intelligent DevOps engineers to ensure that whatever we are upgrading will work seamlessly in production environments, which is why you are always testing these things in your development workloads first. So in this example, we'll be using 1.13.0, which is n-3, n being the latest release, and we are using 3 under that. So let's go to our Chrome browser, and here I'm saying helm install this controller. In the kube system namespace, cluster name is cloud with varjosh-ingress-demo, and then set service account create is false because we have already created the service account. Again, set service account name, this is the name of the service account that we just created. Version we want to use is 1.13.0. For stability, we are choosing this release. So I'll copy this, and then I'll come here, I'll paste this here, and I'll press enter. Now I want you to know that we are installing this in the kube system namespace for Helm. So understand, and we discussed this in our Helm lecture, that if I just run Helm list, I won't see this release. I'll show this to you once this is done. If I run Helm list here, I won't see anything because it is installed in the kube system namespace of Helm. So if I press the up arrow, I write -a, a is for all namespaces, then I will see that there is a load balancer controller which is created here. So understand these nuances, okay? So now let's run kubectl get deploy -n kube system. Like I told you, the controllers are often deployed as a deployment, and if I see the deployments of the kube system namespace, you see AWS load balancer controller. It has 2 pods, and both of these 2 pods are in ready state. So our controller is successfully deployed. Now we understand the role of this controller. Whenever this controller will see an Ingress resource, it will create a load balancer for us. And how do we know it will work seamlessly? We know that because this AWS load balancer controller has a service account mapped, and that service account has an annotated role which must be assumed to create the resources in AWS. And if I run kubectl describe deploy -n kube system, and I write the name of this deployment and I press enter, then you can see the service account that is mapped onto the pods that will be part of this deployment. So if I scroll down here, it is service account AWS load balancer. It is so soothing when you know how everything is working under the hood, and only when you know these things you will able to troubleshoot the real production scenarios. So stay with me. Whatever I'm doing, copy that into your environment, see how everything is working. If you have any doubts, reach out to me, reach out to your colleagues, but don't leave the doubts hanging. Now let's do one thing. I will now clear my screen. I think I've shown you whatever I wanted to show here. Now let's do one thing. I'll go to the diagram and let's create this infrastructure now. So I'll go to my Visual Studio Code again. I will expand demo 1. The first one is 01 namespace.yaml. Here we are just creating a namespace. And why we are creating a namespace? Because I want this to be engraved in your brain. Even when you are practicing, always try to segregate things into namespaces. So let's go back to the terminal. I will cd into demo 1 now, and then I will write kubectl apply -f01. Yeah, now let's do one thing. Now I've created the namespace, but by default my commands won't run in this namespace. So what I now want to do is I want to run kubectl config set context. I want to set the context for current context, and for the current context I want the namespace to be app1ns. I'll press enter. Now what this is doing is whatever the commands I will now run will by default run in app1 namespace. If you have any confusions about Kubernetes configuration files or Kubernetes context, then go and watch the lecture that I have linked in the description. I can now run kubectl get pods and I should not see anything because there are no resources that exist in the app1 namespace. So I'll go to my Visual Studio Code again. Now let's go to the iphone.yaml. So what we are doing here, we are creating a deployment. The name of that deployment is iphone deploy. The namespace is app1 namespace. This deployment will have 2 replicas. Selector is iphone page, template, metadata labels, app iphone page, spec. This is the important part. Topology spread constraint. Here is the point where I'm telling the scheduler that you want to segregate the pods part of this deployment based on the topology key called topology.kubernetes.io/zone. Now topology key can be thought of as fault domain. If I would have provided node here, then it would ensure that all the pods part of this deployment are in different nodes. Now since I have supplied zones here, this will try to distribute the pods on different zones. We only have 2 zones. Hence, if there are 2 pods created as part of this deployment, they will be scattered across both the availability zones, which is 1 in each AZ. And if I run this command kubectl get nodes to labels, then what you see here is this is the topology key that we are mentioning there, topology.kubernetes.io zone. We are mentioning this here, which says that the pods that you create should be distributed across 2 availability zones. If we had 3, it would have distributed across 3. If we would have had 4 AZs, then it would distribute across 4 AZs. Now, when unsatisfiable, I'm saying schedule anyway, but another option that you have is do not schedule. So do not schedule is a hard rule. Schedule anyway is a soft rule, which is a little lenient here. Now maximum skew defines the degree to which pods may be unevenly distributed, and I will let you read more about this, but for now understand that this number cannot be 0, so I have kept this as 1. Now what are the pods that will be part of this? I'm saying any pods that have app is equal to iphone page label, and we know that the pods that will be created by this deployment will have app is equal to iphone page label. Hence we are showing this here. Now we are saying containers. Name of the container is python http. Image that we are using is python alpine. Command that we are using is this is the argument. Now again, I am simulating this. So whenever these pods are hit, these pods will serve iPhone users welcome to cloud with Varjosh. That's it. Now again, what I am also saying here is I want you to make a directory -p iPhone and echo HTML entire this whatever I am writing here, this part into iPhone index.html, because I want this to be part of a directory called iPhone, and in that iPhone directory I am placing index.html, and after that I am running an HTTP server on port 5678. I want you to understand this is a dummy way of representing what we are trying to do. When you are working with real applications, you will have a similar structure. It is just that your image will actually be running the actual application. Then what I am doing is I'm saying that the ports on which my container is listening, on which my application is listening, is port 5678, and we have defined our application to listen on this port. In case you want to play with this, you can even change this and this. So if you change this to, let's say, 789, then this should also be 789. You understand that thing. Here is a service. Important part is annotation. Rest is pretty generic that we have seen since the beginning of this course. This is service for iPhone. We are deploying this in app1 namespace. Annotation is, this is important for health check, and when we move to the Ingress manifest, you will learn it in a better way. But for now, understand that the load balancer, when the load balancer will perform the health check, it will perform the health check on this path, iPhone index.html, and index.html resides in /iPhone directory. We know that because that is how we have configured our application, and we will zoom into this a little more later. Selector, we are saying select any pods that have app is equal to iPhone page label, and here you can see our app has this label, app is equal to iPhone page. If I come down, this is a cluster IP service. Type is cluster IP because we have not defined the type. Then the default is cluster IP. The port is 80. The cluster IP port is 80, and the target port on which my containers are listening is 5678. So this is extremely simple, and we have done this a million times. So similarly, there is Android 3. Everything is similar, if not same. It is just that here instead of iPhone we have Android, and the nomenclature is also done in such a way. So there we had /iPhone /index.html. Here we have /Android /index. The desktop service is a little different only when it comes to path. Here the index.html resides in the root, and we will understand why this behavior is in a little while. For now, just understand desktop is for catch all. If someone is not specifying iPhone or Android, then they will land into our desktop site, and our desktop site is also serving the similar page, desktop users welcome to cloud with Varjosh. And service, here again they were monitoring a specific path. Here we are just monitoring the root, which is /index.html. Rest, pretty much everything is the same. So let's go back to our terminal. Let's clear the screen and let's run kubectl apply -f02, that is iPhone, 03 which is for Android, 04 which is for desktop. Now let me run one thing. kubectl get pods -o wide. Android has 2 pods like we mentioned, and both of these are running in different nodes. Similarly, desktop has 2 pods and they are running in different nodes, and both these nodes are part of different availability zones. iPhone, it has 2 pods running in 2 different nodes. Now let's do one thing. I want to show you the label of the node. So let's go to the console of the screen, because we want the split to be based on availability zones. I want to go to EC2's screen. I will open this in new tab. I will go here and then let's go to instances, and I want to sort these instances based on availability zones. So they are already sorted based on AZs. So if I scroll here, I don't see the, oh, I see the IP address here, 87.177.90.241. So if I go to my Visual Studio Code, what I will do is I will go to iPhone service and I will change this replica count to 10. I will save this, and then here I will run kubectl apply -f02 iphone.yaml. Now I have created 10 replicas. What should happen is 5 of those should be in AZ1 and 5 of those should be in AZ2. That is what the topology spread constraint that we have defined in our manifest should be doing. And this is right under the spec section. And if you go to the references of this lecture, you can read more about topology spread constraint. Now let's go back to the terminal and let's run that command again, kubectl get pods -o wide, and I'll press enter. And you see here are my iPhone pods, and let's see where they are distributed. So I can see that they are spread across multiple nodes, and if I have to segregate the nodes based on AZs, then 77,241 are part of one AZ and 2199 are part of second AZ. So 177,241, there should be 5 instances, 141 and 177. So 177, 241, 241, 177 and 241. So 5 pods are in these two nodes which are part of AZ2A, and another 5 pods are part of nodes that are part of 2B. So understand this, when you are using 2 availability zones, you want your pods to be spreaded across those 2 availability zones. For that, this configuration topology spread constraint can be used. Now that we have understood this, let's change this replica again to 2. I'll save this and then I will apply this file. So this will ease our work as we progress with this course. Now if I run kubectl get pods, I see there should be 6 pods, 2 part of each deployment. So they are terminating right now. If I run kubectl get svc, I should see 3 services, Android, desktop and iPhone. Now I want you to know one more thing. So let's go to our diagrams again, and here we are. And if I scroll down, I have shown a generic traffic flow, and I don't want you to concentrate on the traffic flow right now. I want to show something else to you. So here I have shown that Shwetangi is accessing /iPhone because Shwetangi uses an iPhone. If someone uses an Android, they should be adding /Android. But is this the way how applications are deployed? I never type /iPhone if I'm using an iPhone, or I don't type /Android if I want to access an application from my Android phone. It doesn't work like that. But why are we mentioning this here? I am mentioning this here so that you can understand the concept properly. But I also want you to know how real application development works. When you are dealing with production applications, you will download an app in your iPhone. And whenever you download that app in your iPhone, that will automatically have that URL. You will not have to type /iPhone. Similarly, if I'm using an Android phone and if I download something from the Play Store, then that application's homepage will automatically be set to /Android. I will not have to type /Android. So keep that distinction in mind. I am specifying this here so that you and I can visualize this in a proper way. But actual applications are not deployed or designed like that. But Varun, why do I have desktop here. I have desktop here because if someone is accessing my website from their laptop, let's say they write myapp.com, then they should be redirected to a service that is serving all my laptop and desktop users. Hence, we have a desktop service here as well. So keep this distinction in mind. iPhone or Android users will not be typing this path here. Now that we have that understanding, let's conquer our Ingress manifest. Now, when you look at this Ingress, keep this in mind that whatever you are defining here is directly or indirectly the configuration that you need for your load balancer. So if you have used application load balancers in AWS, you create target groups, you create a load balancer, you create health checks. It is just that you are now defining those things in this YAML. Everything else is the same. Now, if you want to see the documentation for all these annotations are part of a documentation from where I have picked what I need. Now, if you understand annotations, you know that annotations are used by external tools or our external users to know what this YAML is all about, right? Third-party tools like even CI/CD tools can use annotations and take decisions based on what is there in the annotations. So the structure, the general structure of Ingress that you see here is something that Kubernetes has defined, because remember, Kubernetes Ingress is a native resource. So if I go to my Chrome browser and I go to docs.kubernetes.io, and then here if I search for Ingress, I go to the first link here, and if I scroll down, so whatever you are seeing here, this is similar to that. Just get rid of the annotations for now. Networking, Ingress, metadata, all these are same. And here is the spec section. In under the spec section, you have different rules, and similarly you have the spec section, you have Ingress class name, you have rules here. So this structure is defined by Kubernetes, and we can know about this API version and kind if I run kubectl API resources as well. And we have seen that multiple times. So if I go to this screen, if I run kubectl API resources and I grep for, let's say, Ingress here, then these things are already defined here. What will be the kind? Is this namespaced or not? What is the API version? What is the short name? All these things are defined here, and that is what we are defining here. And this structure is already provided to you in the Kubernetes documentation. You do not have to memorize this structure, but what changes is annotations. So annotations is the part where different vendors have written their logic. Based on what you have defined in annotations, the controller will work with the cloud provider or your platform provider to provision a load balancer for you. Understand this important distinction. The structure of this file is already defined by Kubernetes. What you are doing is you are just playing around with annotations to ensure that the load balancer part of your platform, for our example, let's say it is Amazon, so we will define the annotation that are understood by application load balancer offered by AWS. Now, another point I want to make here, I'm making it here because I might forget it later. If I talk about this load balancer that we are creating in AWS, it is not just HTTP load balancer that you can create using the controller that we have deployed. So we have deployed AWS's load balancer controller. AWS's load balancer controller can be used to deploy both network load balancer and application load balancer. In our example here, we are deploying an application load balancer, but keep that distinction in mind that you can also use this to deploy a network load balancer. Now let's go back to our Visual Studio Code. So let's see what we are saying here. Here are the ingress controller setting. ALB.ingress scheme is internet facing. I want my load balancer to be internet facing. The name of the load balancer should be cloud with varjosh-ingress-demo1. Target type is IP, and we will see what IP is in a little while. The another option you have is of instance, and this is extremely important and this needs special emphasis, and we'll see this as we progress with this lecture. Now listener port, right now we are saying only listen on port 80. When we'll move to demo 2, we will also add 443, because who does HTTP in 2025? No one. Then you have health check settings, and these health checks are for your target groups that you create in AWS. Now, what these are, let's understand them. Health check protocol is HTTP because, hello, we are using layer 7 load balancer and it can perform HTTP health checks. Then why not perform HTTP based health checks? Health check port is the traffic port. Then health check interval second. So after every 15 seconds, you are supposed to perform a health check. Health check timeout second is 5 seconds. If there is no response received for a health check even after 5 seconds, then consider that timeout. Then health check threshold count is 2. If there are 2 timeouts simultaneously, that is 10 seconds, there is no response, then you consider that unhealthy. Oh, what I just said is for unhealthy threshold. For healthy threshold is 2 consecutive health checks successful should be considered a healthy endpoint. Success code is 200. Since we are running HTTP, 200 is a success code. Now let's understand what is happening in the spec section. In the spec section, we are saying Ingress class is ALB. What is Ingress class, Varun? So let's move to our diagrams, and I want to take you back to day 27. In day 27, we were discussing storage classes, and we said you can have multiple storage classes based on your requirement. For example, if you want to use block storage offerings from AWS, you can have a storage class that caters to GP3 volumes, and then you can have a storage class that caters to IO1 volumes. And when there is a PVC created, that PVC can call the storage class that it wants to use, and a storage from that storage class will be provisioned. So in this example, we are saying give me a GP3 volume, because here we are calling the GP3 storage class. So a 10 GI volume from GP3 will be created for this PVC. This part is understood. If this would have supplied this storage class's name, so EBS SCIO1, then IO1 would have been provisioned. But what will happen if they do not specify anything here? Then if you have this annotated somewhere in any of the storage classes, is default storage class true, then even if a PVC is not defining a storage class, it will get the storage from the storage class which has this annotation under it. Extremely simple to understand. How is this related to Ingress class? Ingress class is the same concept if you look at it. In Ingress class, there could be a scenario when you are using multiple load balancers. For example, for application 1, which has a specific requirement, you migrated that from on-premises, and that application has heavy dependency on Nginx load balancer. In that scenario, you will have 2 load balancer controllers in your cluster, one for application load balancer of AWS and another for Nginx's load balancer. In that scenario, you will have to specify the Ingress class name. Ingress class name as in, if I want to use AWS's ALB, I can just supply ALB. And why is this ALB? Because when you install this controller using Helm chart, a Ingress class is automatically created for you. If I run kubectl get Ingress class, then you can see here that an Ingress class named ALB is automatically created for me. I can also run kubectl describe Ingress class and name of this Ingress class to understand more about this Ingress class. So for now, understand that you can have multiple controllers in your cluster, and those multiple controllers can be configuring their respective load balancers. Now, as you were defining in the storage class, so if I go back to the storage class part again, here you were defining which one is the default storage class. Similarly, here you can define which one is the default ingress class as well. For now, I have not defined it because I only have one load balancer controller, which will be just creating AWS ALB for me. In case you have multiple load balancers, multiple load balancer controllers, then you can configure this accordingly. In that scenarios, in the ingress class manifest, you will be annotating which one is the default, and once you add that, if you have defined a default ingress class, then this field is not mandatory, which makes sense. Now is the chunkier part. We have defined rules here, and these rules are HTTP based, and then there are paths. As the name implies, these are paths. What are paths? There is a slash iPhone path, there is a slash Android path, and then there is just a slash path. So let's first discuss about the path that is forward slash iPhone. The path type is prefix. Now this is important, so let me copy this. So prefix is when you want to be a little lenient, which is mostly used in production environments because you do not want to, tighten the users to always type the exact thing. So what I can do is I can type this here, the URL, and here you can see when it is a prefix, it is a little lenient. So even if it is forward slash foo and user types forward slash foo forward slash, then also it will work. But if you are using exact instead of this prefix, then what will happen is if you have defined forward slash foo and the user types forward slash foo forward slash, then it will not work. So you may not want to be that strict. Hence, I have seen prefix being widely used. And there is one more implementation specific. If your load balancer controller uses it, then you can see in its documentation. So let's go back to Visual Studio Code. And then what we are saying is backend. So this is the important one, which is the service that will be serving forward slash iPhone. And here we are saying the service is iPhone service, and that service is listening on port 80. And that is what we know, the service that we have created is listening on port 80. Then we have path for Android, exactly similar. We have Android service, and this service is also listening on port 80. This is the port of the cluster IP service, and the cluster IP service is listening on port 80, and our container or our application is listening on port 5678. I have deliberately made my application to listen on 5678 so that you can see this distinction clearly, and this will become more important as I show you how the load balancer looks when it is created in the cloud platform. Then we have path. This one is catch all. So if the user does not specify iPhone or Android, then they will be served by desktop service, which is listening on port 80. Again, I'll go to the terminal. I will run kubectl apply -f, and then what do I want to apply? 05 ingress.yaml. I'll press enter and it will work. Now I want to bring an interesting point here. Throughout the demos that I perform, I run the YAML and it gets implemented and there are no errors because I have rehearsed, I have tamed, tuned, tweaked these YAMLs multiple times before recording this session. So it works for the very first time. But in reality, it does not work like that. You will be playing around with the configurations, you will be looking at the documentation, you will be using generative AI to streamline your YAMLs and so on. So keep that in mind. Not everything works at first, and if it works at first, then awesome job. or maybe it is beginner's luck. But you know, streamlining things take time. So if your YAMLs are throwing errors, do not get disappointed with that. Okay, now we have created our Ingress resource. As soon as we created our Ingress resource, our controller who is watching our Ingress resource would have created a load balancer in the cloud. So let's do one thing. Let's look at that load balancer. Firstly, let's run kubectl get ingress, and you see there is an ingress with demo1 created, and there is the address of the load balancer that was spun in the cloud, and it was spun 89 seconds back. You see how fast it is. My controller is continuously watching the ingress resource, and as soon as it saw there is an ingress resource created, it created a load balancer in the cloud. That is how quick these things are. Controller is continuously monitoring the ingress resource. Now let me run kubectl, and all these things are created in application one namespace. Remember, the best practice: contain things pertaining to an application into a namespace, and here we have done exactly that. And I have configured my current context to point to application one namespace, which is why I do not have to add -n flag again and again. So I will run kubectl describe ingress, and what is the name of my ingress that I just created? It is called ingress -demo1. I'll press enter, and you see whatever we have defined in our YAML can be seen here in a tidy format. If someone accesses /iPhone, direct to iPhone SVC, and these are the two pods that are for iPhone SVC. Anything for Android SVC, and these are the pods for Android SVC, and so on. And here whatever we configured as annotations can be seen here, and this is what you want to see: successfully reconciled. Now let's go to the console and see what is happening there. Okay, so I am in the AWS console now, and I will go to the EC2 section, and from here I will navigate to load balancers, and I see there is a load balancer created which is internet facing, like we defined in our manifest. This is part of this VPC. Understood. There are two availability zones across which this load balancer is spread. Then there are two security groups associated with it. There is the DNS name. Here is the on, and it was created on 4th of August. Let's click on this. We see here are the details. This we have already seen. Listener and rules. This is an important part. We defined port 80 to be a listener. Only one port was defined because we are just doing HTTP right now. So if I scroll up, we defined only one listener, and we said this should be internet facing, and that is what we see here, internet facing, and this is the listener port. Then there are 4 rules. So there is a default rule. This will not be used here because these 3 will always have priority. Now I want you to know that always keep this catch-all rule at the very last. Now previously what happened was, if this was typed at the very top, this used to appear in the same way in your console. But now I think things have changed. Even though if I pasted it at the very top, this still appeared at the last, which is a good thing. But to maintain sequence, have this catch-all at the very last, add more specific rules at the very top. So we know iPhone and Android are specific paths. Hence, I have written them at the top, and then there is the catch-all path. So here similarly, there is priority 1 given to /Android, and this anyone could have any priority. That does not matter, because if they are accessing Android, they will be served by Android. If they are accessing iPhone, they will be served by the iPhone path. So priority 1 is this, priority 2 is this, and then priority 3 is catch-all. That is how it should be. Now I want you to know one thing very clearly. When I talk about AWS's load balancer, it works on the concept of target groups. Now what happens is each load balancer has a target group, and what is happening in this screen is, if I go back to Visual Studio Code, all these paths that we have created are mapped to a target group. So if I have created this path, and see, this is paths, there are 3 paths defined here. The first path corresponds to a target group. Similarly, second path corresponds to a target group, and the third one also corresponds to a target group. Now here the target group, what they are doing is, if the request is received to the iPhone target group, they will forward the request to the iPhone service. And if I go here, you see that forwards to target group, this one. And let me show you one thing. If I go to this target groups and I click here, let me click on iPhone first, and if I click on iPhone, the status is healthy. And if I go to targets, you directly see the pod IPs here, though the traffic is not going to cluster IP, it is directly going to my pods. So understand one thing, the cluster IP service that we created here is just used to create a target group and tell that target group what are the pods that are behind this service. And who are the pods that are behind this service? The pods that are part of iPhone deployment are behind this service, and the IP of those pods are 77 and 156. So if I go to my terminal here and I write kubectl get pods and I press enter, I have to add -o wide if I want to know the IP addresses of the pod. You see here are the iPhone pods 77 and 156. 77 and 156. So what is happening here is traffic is directly going to my iPhone pods. And if I talk about Android, similarly for them, the traffic is directly going to 115.0 and 74.149. And if I look at Android, 149 and 115.0. So traffic for all these target groups is directly going to the pods. And you can also see here is the port number, and this port number is the port number on which my application is listening. Why is traffic directly going to the pods? This is something which is extremely important to understand. We are using the VPC CNI plugin here. Amazon's EKS cluster comes by default with AWS's VPC CNI, and when you are using that VPC CNI, you can interact directly with the pods on their IP addresses. And if there are any dots that are not yet connected, I will take you to a diagram where I will explain this step by step what is happening. But I want to explain you right here with a functionality that AWS offers. If I go to the resource map and I scroll this to a little down, here you see this is my listener which is listening on port 80, and then you have the first rule, and this rule is for my Android service. So if I click on this rule is telling me if someone comes here, I will send that to target group, this target group, because they have specified /Android. And then who are the targets that are listening for this /Android? It is these 2 targets, and these 2 are the pod IPs. Now let me take you to the diagrams. Here I want to explain why first this is going to IP. This is going to IP because this is what we defined. Target type is IP. The other option is instance. If you would have defined instance here, then you had to create a node port service firstly instead of cluster IP, and then instead of these nodes, instead of the pod IPs here, you would see your worker nodes. Now let's understand this with the help of a diagram. So if you see this diagram, this is exactly the configuration that we have. Shwetangi will access load balancer's DNS name /iPhone. It request will via the internet come to the load balancer. Load balancer is intelligent. Load balancer has target groups, and based on the rules that are configured at the load balancer level, the iPhone request will be served by the iPhone target group, and the iPhone target group will directly send the request to pod IPs. I want you to clearly understand the service, the cluster IP service that we created was just used to create this target group and to tell this target group which are the pods that are sitting behind that service, because that service had that details. But after that, once this target group was created, the target group is directly interacting with the pods, and that is what I showed you just now in the resource map in the load balancer section. So keep this thing in mind. When you are using target IP, you do not have to create a node port service. A cluster IP service would suffice. And here are the key pointers. The first point is Kubernetes service is used only to identify the backend pods. That is what I told you. ALB forwards traffic directly to pod IPs, which results in fewer hops. Now, third point is a critical one. Requires correct security group rules on the node ENIs, which are automatically handled by the AWS load balancer controller during ALB provisioning. This is automatically handled, but I want you to understand this. My pods are running onto my nodes. If my load balancer wants to interact with my pods, my nodes on which my pods are running first allow that communication. Hence, the security group of my nodes must allow inbound from the load balancer. And here they allow inbound from load balancer security group, and I will show that to you in a little while. But for now, look at this flow. Shwetangi will access this request via the internet, will go to the AWS's load balancer, then to iPhone target group, then pod IP via nodes ENI. That is why I want to allow that communication, and then finally to my iPhone container, which is listening on port 5678. As simple as that. So now let me take you to the console, and here first I want to show you the security groups associated with my load balancer. The one is 64A and 6B3. Now let's go to the instances here. I will choose any one instance. I'll go to the security of that instance, and here I know these are the inbound rules, and this is the inbound rule I'm interested in. This is allowing port 5678. The source is any security group with ID 64A. 64A is a security group associated with my load balancer, and here I am allowing inbound on port 5678 on my worker nodes. That is the reason this communication will work. Now, if you have any confusions about inbound, outbound, again, go and watch the network policies lecture. We covered those things in detail there. But here, now I want to show you another scenario, what else you could see in production environments. Here is another one. If we would have created a node port service instead of cluster IP. Now, when you are using a third party CNI because of XYZ reason, in that scenario, you will have to use instance as the target type. Now, why you would have to use instance? Because the VPC CNI, it understands pod networking and it can directly interact with the pod IPs. Other CNIs do not have that capability yet. Hence, you will have to use instance, and when you are using instance, you will have to use node port service, because there must be some way via which a entry can be made inside the cluster. And we know if you cannot directly access pods, then you will have to go in the cluster via the worker nodes. And when you involve worker nodes as well, you add an extra hop. So let's see what is happening in this diagram. First, the request will come to the load balancer. The load balancer will say, okay, this is for iPhone. It will send it to the iPhone target group, and the iPhone target group, right now the targets in the target groups are the pod IPs for those respective deployments. But with this scenario, the target IPs would be of all the worker nodes, and there will be a port exposed that is in the range of node port. Let's say it is 31,000. The traffic will first come here, and then, like node port works, there is a node port that is for external traffic. Then the intra cluster communication still happens over the cluster IP service. So here is the node port service. Node port service will direct that traffic to the cluster IP, and then cluster IPs will finally load distribute the traffic, and at the very last the traffic will reach the container on port 5678. So understand this flow. ALB routes to EC2 node port, traffic goes through kube proxy, adds extra network hops and latency, works without VPC CNI, suitable for Calico, Weave, etc. So the request here comes from Shwetangi, then over the internet it reaches the AWS's load balancer, then iPhone target group, type instance, then EC2 nodes on the node port, then kube proxy. Now we know that cluster IP is performing the load distribution. All of those functionalities are there because of kube proxy. And finally the request reaches the pod IP, and then finally the request reaches the iPhone container, which is listening on port 5678. I hope this flow is understood, and you will be seeing this design as well in your production clusters. And not just with a custom CNI, a lot of clusters are there who are using this design even when they are using AWS's VPC CNI. Now that could be because of lack of knowledge, or maybe when they were deployed their cluster, this functionality was not available. There could be numerous reasons for that, but I want you to understand that when you are using VPC CNI, this is the design that you should prefer. Now let's test what is happening. So I'll go back to the AWS console again, and I will go to my load balancers. Now let's copy this name. I will paste this here. Your browser could be adding HTTPS automatically. I want to specifically say that this is HTTP. Do not worry, in the next demo we will be fixing this. And I'll press enter, and you see desktop users, welcome to cloud with Varjosh. Now I have not supplied anything, which is why it went to catch all. Now if I add here iPhone, this will go to our iPhone users, welcome to cloud with Varjosh. And similarly, if I add Android here, this will go to our Android users deployment. So this is being served by our Android pods. This is extremely simple. I hope you have understood what we have done in this lecture. If you intend to watch part 3 later, remember to delete your Amazon EKS cluster, because you pay an hourly charge for your cluster. That wraps up part 2 of our Kubernetes Ingress series. We set up an Amazon EKS cluster across multiple AZs, configured the AWS load balancer controller, and deployed a path-based routing setup using Ingress and ALB. the kind of configuration commonly seen in real world Kubernetes environments. In part 3, we will look at enabling TLS for our web application, registering a custom domain, and name based or subdomain based routing. If you have any questions, feel free to ask them in the comments section and I will reply. If this helped, do consider liking, sharing, and subscribing. It will mean a lot to me. Thank you very much.